Welcome to ThinkTech Talks here on a given Monday. I hope you had a good weekend. We're back again with more. We have 4 streaming talk shows every day, 20 a week. We're very ambitious, and we broadcast them to the world on ustream.tv and Spreaker.com for audio, and the links for those are on thinktechhawaii.com. We ultimately post them on YouTube. They all get posted on YouTube, so if you guys want to see yourselves, you can go to YouTube. And we put them on Olelo 54. To introduce, we have Bruce Howe and Patty Fryer of SOEST, the School of Ocean and Earth Science and Technology at UH, a very famous school. May I say world famous?
Yes.
It's doing fantastic things and making UH famous. All of us famous, actually.
Oh, yeah.
So can we do self-introductions? Bruce, will you start?
Certainly. I'm Bruce Howe. I'm a research professor in the Ocean and Resources Engineering Department in SOEST. And my specialty is, well, several ocean acoustics, and then also what I call sensor network infrastructure. So things like cable systems and underwater gliders, basically trying to make the widgets and provide the widgets for other oceanographers to use to observe and measure the ocean.
How did you get into this area? It's so exotic. Whenever I talk to one of you guys, I want to sort of reel the clock back and start my education again.
Yeah. Well, I've always been interested in the ocean, and I think, it goes back to Jacques Cousteau. And, but undergraduate mechanical engineering and then atmospheric, well, I grew up in a research lab, basically, and learned a lot of what I know there.
Where was that?
At Stanford University.
If you're going to pick a research lab, that's a fairly good place.
Yeah. So, and then I went to Scripps Institution of Oceanography.
Another good pick.
Yeah, and learned acoustics basically on the fly there, and basically got introduced to using acoustics to sense the ocean on all scales up to the basin scale and climate and so on. So that is my ultimate passion and reason for doing all the sensor work, is to basically provide the platforms to do the acoustics work from. So I'm involved in several projects that
We'll talk about them
that.
one by
Yeah,
one.
Yeah.
You love your work?
Yes, I wake up and
I knew you'd say that.
I'm anxious to get to work and get things going, and working with great colleagues here. It's wonderful.
So somebody doing what you're doing, are you teaching also, or is it all in the research and writing department?
I do a little teaching, 1 class a year in ocean acoustics, and I think I'm being drafted to teach another teach an undergraduate class next fall.
Oh, that's great.
So
Then you'll have plenty of time to come down here again.
yeah, absolutely.
Okay, Patty Fryer, also at SOEST. So tell us about yourself.
Well, I am a research professor, and I call myself a marine geologist, and I'm interested mostly in what happens at places where the ocean crust is forming and also where it's being consumed. So mid-ocean ridges, the trenches of the world, and in particular out in the Western Pacific, I've worked for 40 years or so on the Mariana Trench, which is the deepest trench in the world's oceans, looking at the interaction between the ocean water, the rocks and sediments on the seafloor, and how all of those processes influence things like microbial communities, although I'm not a biologist.
Well,
but
leave
I
that
work,
to Dave Carl.
yeah, absolutely. And I'm interested in the overall processes, including the kinds of things that will prompt earthquake events and the tsunamis that are generated by them that create natural hazards, of course, that everyone's interested in. But the coolest thing I like to do is dive in submarines.
Ooh.
So I've been in the Alvin submarine, which is the U.S. academic submarine, and also in the Japanese Shinkai 6500. So that, I think, is probably the most exciting part of the work I get to do.
Yeah, wow. Okay, I feel like we've exposed the canvas. Now we're going to dive in. Sorry to use that expression with you guys. Well, talking about projects now for a minute. Wow, I'm really excited about this. The cable.
Yeah. So I'm the PI, principal investigator on the Aloha Cabled Observatory project, and this rests on the shoulders of many, many people over decades, really. Fred Dunabeer at the university and Roger Lucas and Dave Carl started this 2002, and we finally installed this observatory in June of 2011, and it's still working. There are a few minor problems.
Underwater observatory?
Yes. So this is using a retired submarine telecommunications cable that goes out of Makaha on the west side of the island and goes 200 kilometers, ending up 100 kilometers north of Oahu in almost 5,000 meters of water. It is the deepest operating cable observatory in the world. And so we have some basic, relatively simple sensors out there now. And the reason it's there is because of Station Aloha. Roger and Dave started this program 25 years ago to make repeat measurements there every month with a ship. And the idea is with this cable system, we can support robotic systems to complement and hopefully take over some of the routine tasks and leave time and money for the people to do more intense, process-oriented experiments.
This is a platform that gives you huge possibility.
Right. So it's basically plugging in your wall socket. You can plug in for power and internet connection down on the seafloor. And so right now we have live streaming audio from a hydrophone, and we have a camera working, but unfortunately the lights are not working at the moment.
Maybe we can help you here.
But we expect to go out next month to put in a new system and more lights and fix some things. And
How deep again?
4,728 meters, which is roughly 3 miles.
Wow.
deep.
But you couldn't actually take a dive. You couldn't take a dive down. Not your own self.
No.
You have to have a bathysphere of some kind to go down there.
Well, we use remotely operated vehicles, ROVs, which are tethered to the ship, but they're small car size things that have manipulators and cameras.
This is
and
not
so
the
on.
Pisces.
No.
Pisces twins, I call them. Yeah.
Those are man submersibles. This is still robotic, and it can go deeper. And University of Hawaii just got a new one, and we're in the process of testing it. And this cruise to service the Aloha Cable Observatory will be the first sort of operational science cruise for it. So the end goal, the main purpose for Aloha Cable is to support all this other science that goes on at Station Aloha as part of the Hawaii Ocean Time Series and all the ancillary projects that sort of cluster around that.
So this actually is a great location for this kind of science. I mean, being in Hawaii.
Absolutely. I mean, in Hawaii, we have to capitalize on our location, and this Station Aloha is representative of, I'm not quite sure the number, but 50% of the ocean is similar to the ocean around Hawaii. It's basically desert, and so the measurements they make are crucial to understanding a large fraction of the world's ocean. And there are different ways of observing the ocean, and this is one of them. There are other things. Well, I also do these underwater gliders that make temperature and salinity measurements.
What's an underwater glider? Is
Well,
it like what I can buy at the toy store?
Well, it's a little bigger than that. It's
Costs a little more.
person size. Yeah.
Not made out of balsa wood, right?
No. These little robotic submarines, basically, that pump oil in and out to change their buoyancy and sink or rise up. And they glide, basically, very slow, half a knot or half a mile an hour. And they go down roughly 1,000 meters and come up. And on the way, they measure temperature, salinity, oxygen, and biological.
No
things.
engines on them? No motors or anything?
No, there are no external moving parts.
And when you're done, you just pull it up?
Well, you have to typically you go out in a boat and pick it up, or if you're lucky, you can direct it to come to near shore.
Well, you can control the control surfaces on it.
Well, yeah, it changes buoyancy up and down, and then it has the battery inside can move forward and aft to change its pitch, and therefore it can dive down, move the battery forward, and then come up, pump out oil and move the battery back, and it goes up. When it's at the surface, it communicates by satellite telephone, and it has GPS. So each time it comes up, you know where it is, and you have the opportunity to give it a new target to go to, or it'll have targets stored already, and it'll continue on.
Well, this is great,
So.
I think the public needs to know everything about this. It's so interesting. So you guys, you collaborate? I mean, you see each other in the passageway.
Oh, yeah, a lot. We collaborate on committees. But we also are, we're working together now to try to get new sensors for the new ROV that SOEST has acquired. And because it will be really the capable ROV for this portion of the Pacific as well as the Western Pacific, the more we're able to do with it, the more people will want to use it and be able to come out to Hawaii.
Then collaborate with other schools.
Oh, yeah.
SRIPS, for example, could come around and all that.
Absolutely,
Yeah. This reminds me, though, of the Israelis. I'll tell you why. Because they bought American jets, fighter planes, right? And there were problems. They didn't have all the functionality they wanted. So they started modifying the planes.
Yeah.
For example, they invented the rear view mirror. Took a rear view mirror out of a car, put it in the jet plane. Now the thing works better, and then the American Air Force, adopted the same improvement, that kind of thing. But it just strikes me, whenever you get a piece of equipment, you're going to modify it because you're scientists.
Yeah.
You always are going to improve everything.
Well, that's what we hope, and we're hoping that, in fact, with the new technologies that are coming on board now, that we'll be able to go to greater depths than we are currently capable of doing, and with tools that we might be able to design to go to, say, full ocean depth, like 11,000 meters.
Wow.
These
That's the deepest you could possibly find in the world.
That's right. And if we can get instruments that can be utilized at those kinds of environments, then those would be so small, so efficient, and so portable that you could put them on all of the existing vehicles and increase the capability of those vehicles.
And you're always looking to do that because you want to make the best platform. Because because if you make a better platform, you can do more with it, and better metrics and all that.
Yeah, and you can get more rocks from the seafloor, which is what I want.
On that note, we're going to take a short break. Nothing about the rocks.
Okay.
So that's Bruce Howe and Patty Fryer from SOEST, the School of Ocean and Earth Science and Technology. It's right up East-West Road, and you turn left. Am I right? It's right. Am I right? Is it? Yeah. Maybe I'm thinking of the.
Yeah, that's it.
Okay.
Yeah.
And at UH Manoa, one of the leading research elements of Manoa. This is ThinkTech Talks. I'm Jay Fidell. I can my own name. I'm Jay Fidell. We'll be right back after this short break.
We want to thank our underwriters. Hawaiian Electric Company and its affiliates Maui Electric on Maui and Hawaii Electric Light Company on Hawaii Island are deeply committed to the communities they serve. Galen Ho is a senior executive of BAE Systems, a global defense, security, and aerospace company. The High-Tech Development Corporation, the state's leading technology agency, attached to the Department of Business, Economic Development, and Tourism. Castle and Cook Hawaii, with a time-honored legacy that spans more than 160 years and revolves around its mission of investing in Hawaii, creating communities, and providing for the needs of our state. Hawaii Gas, formerly the Gas Company, a proponent of the Liquefied Natural Gas Initiative, helping Hawaii achieve its transition to clean energy and a better energy future. Collateral Analytics, a Hawaii-based tech company empowering the real estate industry with greater and faster access to the tools and data they need to make better informed property investment decisions. I'm Nicole Horry. Thanks so much for joining us on ThinkTech. I'm Maria Kashem. See you next time.
We're back. We're live. This is ThinkTech Talks. I'm Jay Fidell. I got that all squared away during the break. I'm here with Bruce Howe and Patty Fryer of the SOEST part of UH. And we're talking about, what are we talking about? Ocean science in the 21st century. I think that was our title. So let's go to the I mean, it's irresistible to ask you about interdisciplinary, connections and cooperation, not only with various elements of UH, but with a global community of science. Because when you guys went to school, when I went to school, it wasn't nearly so global. Now it's all about global.
Right.
But tell us how that works for you.
Well, one example is an experiment. Well, I've been working on these sea gliders, these underwater gliders I mentioned. And so in one experiment, we put them in the Philippine Sea for a year. Well, actually, they were only in 4 months, but other people were there for a year. So those other people were people from all around the country, Scripps, MIT, University of Washington, Hawaii, and so on, with the idea of understanding the interaction between what the ocean is doing and the acoustics. So my little part was putting a receiving hydrophone on a glider so we could listen to these acoustic sources that other people put out. And with that information, we're learning how to do what's called acoustic tomography. So it's just like sort of medical tomography, collecting data along many crossing paths, and you can reconstruct what the field is. In our case, the temperature field. In X-ray tomography, it'd be the X-ray attenuation field, if you will.
Say one more time about acoustics. Why do you care about acoustics in the ocean? This is actually a question for you, but you can answer it also.
Well, my interest is because we can use it as a tool to map out ocean temperature and currents, and therefore...
So you send out a sound wave.
You send out a sound wave, and you measure the time it goes from A to B, and with GPS, for instance, you know where A and B are. You measure the time, you know the distance, you can get the speed of sound, and in the ocean, the speed of sound is related to temperature. So it's a way...
So if it's warmer, then the sound will travel faster.
Right.
If it's colder, slower.
Absolutely.
And you can use the speed of return to determine what the temperature was.
Yep.
Well, suppose there are many temperatures between A and B.
Well, that's why you want to try and get many paths crossing at many different angles so you can resolve that horizontal structure.
And then you use software to interpret all that.
Yeah.
The software is very sophisticated, I imagine.
It is. That actually is. It's both good and bad. It takes a long time to learn how to do that.
Okay.
That reduces the number of people involved in this field. But the long-term goal is to basically be able to measure on basin scale even ocean temperature changes. And the advantage of the acoustics is you can do that very quickly. I mean, sound takes an hour to cross the Pacific Ocean. So in principle, you can measure the whole temperature field of the ocean in an hour.
Sound across the Pacific Ocean? You mean like from the West Coast to Asia?
Yes.
An hour?
Yes.
Even a little sound?
Yeah, I mean, what we do
Has to be
is
strong enough to make the trip.
Yes and no. You send, just like GPS, you send these coded signals. So the actual instantaneous level is not very high, but it's when you average over a long time that you can build up the signal and you can recover the signal.
My curiosity is warming all over me. Does sound behave differently? I know the answer. In water as it does in air?
Yes, in water it travels 5 times faster than in air.
So you see that?
Yeah.
This really helps now. Now we're zooming in on you here.
Right. And it can go farther. There's less attenuation of sound in the ocean.
Okay. You can learn a lot from that.
Yeah, and I mean this is one application of sound in the ocean, and I'm using that same acoustic receiver. You can do many other things. Listen for wind, rain, marine mammals. So these vehicles and other similar things can be used to, in a mobile sense, learn about distribution of marine mammals, for instance.
So it's a big learning tool. Sound is
Yes.
a big learning, it's like
Yes.
seeing. It's
It
like
is.
seeing what's in the ocean.
Because in the ocean, you can only see a very short distance.
Yeah.
And so really you need the acoustics to extend your domain of influence. And I mean, one thing like Patty might be interested, you know, one day there's a vision of mapping in great detail the entire ocean floor. So you take these autonomous vehicles
Yes.
yet to be built, but
Yet to be built.
somehow
You
you're
should
gonna
have it in your mind
Yeah.
what they should look like. Okay.
Absolutely.
somehow you have to navigate them,
Yeah.
you know, over long distance, and you have to communicate with them, and acoustics will absolutely play a major role.
And you
in
don't need wires or anything like that.
exactly. Yeah.
So you were talking before about the glider, and the glider doesn't need wires either. You communicate with the glider by sound?
One can. We have done that. It's not routine yet. There's one major project that will be using gliders to collect data off subsurface instruments, and then when it goes back to the surface, it sends it back by satellite. So it's a gateway. It's a communications gateway device, and I mean, this is one of my passions is looking at really truly the basic kind of infrastructure that we need. We need power, we need communication, and we need precise time. And we want to provide that throughout the entire ocean volume, albeit at different degrees and so on. I mean, at a cable system, we have a lot of power and all those things. You know, with the glider, it's less so. But the whole concept of we need to project that kind of infrastructure into the interior volume of the ocean.
Can I ask him a question?
I want you to add your 2 cents, actually.
Well, what I was wondering was the work that you did in the Philippines, then, does that provide a baseline for return later to see how ocean temperatures may change over longer periods?
Absolutely,
Is that the sort of thing that
yes.
you're working on as well?
And so with all the collaborators, I mean, there are a lot more. We should be able, for that 1 year, we'll have a very detailed oceanographic picture
Right.
built a lot from acoustics as well as more conventional measurements. And so that would be a baseline.
Yeah.
And
Okay,
the thing,
but I'll ask you the old time HPR question. Why do I care?
Your
Well-
Stephen Colbert moment here.
okay, as
It's a real stumper, isn't
we
it?
we have an engineered world already.
Okay.
We just don't know it, and so we will be fine-tuning basically how we interact with the world, and to do that, we basically need to know the state of the entire Earth in order to better, yes, control it, better know its state, and predict, you know, what will happen in the future.
and better adapt to it, which
Yeah.
is probably what mostly civilization is going to have to do, particularly with
Right.
What do you mean by that?
I'm thinking of Bangladesh, and I'm thinking of the islands that we visited on the Cameron expedition, where the groundwater sources are gone because sea level has risen, and it has the groundwater has become more saline. They can't grow the taro that they were subsisting on. They're now subsisting exclusively on breadfruit and fish and what comes in with the
They don't
airplane.
have the fresh water.
That's right.
It's serious.
These people are going to be losing their homes. Nations are going to have to be relocated. So understanding the kinds of things that Bruce is working on, the reason you should care, the reason we should all care, is because it's people's lives that are at stake in many of these cases.
And it's happening.
And it's
Yes.
happening
Yeah.
right now.
So where's the crossover between you on this, on acoustics?
One of the things that I use as a tool is side scan sonar in the oceans to make maps of the seafloor in order to understand the morphology of the seafloor, so that I can then explore it with a variety of things, submersibles, but remotely operated vehicles too I've used.
I've heard the term side scan sonar recently. I'll tell you where. It was about a month ago at Snug Harbor. And these guys, I don't know, it wasn't SOEST, maybe it was. College of Engineering was there. Margot Edwards was there. They were rolling out a gizmo. The name was an acronym. It was an underwater vehicle, harbor security,
autonomous surface vehicle.
Yes, it was surface vehicle.
Brian Bingham.
Yes, Brian Bingham was the principal investigator, or he seemed to be the prize. Yeah. And,
so he I think, put a side scan sonar on that.
Yeah,
Okay.
and he talked about it. That's where I remember
So
it from.
he could map out a harbor, his unit was for shallow water.
Shallow water,
but
just a
high
harbor.
precision, and one application is if there's some disaster, you can go map a harbor quickly with this and see where the wrecks are, and is it safe for a ship to come in?
Contamination, what have you.
Yeah. It couldn't find molasses, unfortunately.
No.
Well, that's true.
Well,
At least
does the
we got
density
instrument.
change enough? Maybe if it did.
Just had to put another sensor on.
Yeah.
That's all.
Right.
Sucrose sensor.
So this is not what you're talking about. Side scan sonar for them is a small thing
Yes.
compared to the way you use it.
Yes.
How do you use it?
Well, what we have used, actually, Margot was in charge of the Hawaii Mapping Research Group for a long time, and what we do is we go out with a vehicle that is towed off the back of the ship about 100 meters below the surface, and it maps the seafloor. It can map out to 10 kilometers on either side of where you're drawing your ship's track.
Yeah.
So you mow the lawn, back and forth.
Systematic
And-
search.
Yep, systematic search, and you create, with these lines of data, you can create a huge map of over large areas of the seafloor, and
And if you're careful, you can see canisters of mustard gas right down there. Am I right?
with the higher frequency ones, yes, you can.
Right.
Yes, and Margot is doing that right now. She's searching for areas that have munitions that have been dumped after World War II and even a little later. But the kinds of things that also can be done with them, take the Japan earthquake of 2011.
Yeah.
It's possible to map, having mapped the area beforehand, to go back and map and see what the change was in the ocean floor that then gives people better ability to model what actually caused the tsunami to form and how large it was, how disastrous it was, even what direction
Sounds
it
like
was
very
pointed.
sophisticated software. You take the
Oh, yeah.
the ripples down there and the topography of it, and then sort of analyze it and figure out the history of it.
That's correct. And by looking at if there's a fault scarp, for instance, and you can tell exactly what direction the seafloor moved in, you can model in real time, if you have that data in real time, what direction the largest amplitude waves are going to go. You may have seen on the web or on TV this very colorful diagram that showed this huge orange, which was high amplitude energy coming toward the Hawaiian Islands after the earthquake in Japan. And those same models exist for earthquakes that would take place off South America or in the Aleutians. And Hawaii is potentially right in the target line of an earthquake that might occur between where the 1946 earthquake occurred that created the tsunami that swept through Hilo and killed so many people, and one's a little further east, and there's a gap in between those two where if there were a large earthquake like that and a tsunami were generated, it would come directly toward the Hawaiian Islands.
This is Alaska.
This is in the Aleutians, yes.
But it wouldn't
off
affect me.
Alaska.
I live up in the hill, right?
I live on a hill too, but
There are a few people lower. Yeah.
On this note, this scary note. By the way, I'd like to, when we come back, I would like to talk about, the weather, and whether with these tools you can predict the weather or see bad weather coming, whether you can see sea changes that are created by bad weather. I don't know the answer. Just interested in the connection there. We'll be right back. This is ThinkTech Talks. We're here with Bruce Howe and Patty Fryer of SOEST. We'll be right back after this break. Aloha, I'm Jay Fidell of ThinkTech. ThinkTech is a 501c3 Hawaii nonprofit corporation. We began ThinkTech in the year 2000. At ThinkTech, we work to raise public awareness about tech, Energy Diversification and Globalism in Hawaii. We do 20 live stream talk shows every business day, and we do a weekly TV show on OC16. We pay the bills with donations from our supporters. Won't you help us by making a donation? All you need to do is go to our website, thinktechhawaii.com, and click there on the Donate button. We hope that you like what we do and that you will support us and help us continue to do it. Thanks so much for watching and for helping. I'm Jay Fidell of ThinkTech. Mahalo.
Ocean Observing System.
We are back here on ThinkTech Talks on a given Monday. We have Bruce Howe and Patty Fryer of SOEST, the School of Ocean and Earth Science and Technology at UH Manoa, and we are diving deep into ocean science. So, I was saying during the break, correct me if I'm wrong, because I know nothing about this. I studied law, nothing to do with it. But, so you have an ocean that has changed in the past, say, 100 years. It is changing now because of, I guess, our human effect on it and all that, and climate change and all that. So it has to be watched. You guys have the ability to watch it, at least in some ways, and what you can learn from watching it can really help us, maybe save us, as the planet changes, because the planet is changing. Am I right? How much of that is right?
Yeah, that's a fair summary. Yeah.
I think one of the things that, in particular, the kind of work that Bruce is involved in monitoring temperature changes in the oceans, something I'm keenly interested in, is on the continental shelves of most of the major continents there are deposits or accumulations of petrocarbons, and these
like oil?
Gases, I'm thinking natural gases, which at the correct temperatures and pressures create a solid layer, basically a gas water mixture, an ice essentially, and these stay stable for eons, thousands of years. But if temperatures change enough to destabilize those things, there could be the effect of huge submarine landslides. There was one 8,000 years ago off Norway, the Storegga slide, which is the biggest slide that has been observed, I think, in the North Atlantic, and it created a huge tsunami that swept across England and Denmark and the Scandinavian countries, maybe as far as North America. I don't think that there's any, for sure, any analysis of sediments.
Is that like the
there
Kailua slide? I don't know if they call it, but you know the one.
I know what you mean. Yeah, off the windward side.
From above sea level
Yes, it was.
into the sea. You're talking about all under the sea.
I am. It wouldn't have been triggered by the same sort of thing. Possibly related to
It's the same
the end
idea.
of an ice age, but this problem of the destabilization of these gas hydrates, these gassy ices in sediment layers is a worldwide problem, and
It's a greenhouse gas.
Yeah, it's a greenhouse gas.
So this is part of climate change.
Absolutely.
Could
And it's
be,
another,
yeah.
we haven't heard too much about this aspect of climate change, but if you have undersea landslides, you
Yeah.
can have terrible results. I mean,
They are tsunami generating events.
yeah. We haven't
And-
had this lately, though.
No. One thing we have had recently, however, on the East Coast was a relatively small tsunami, which people thought might be related to a landslide somewhere, Canary Islands or something, but as I understand it, and Bruce may know more about this than I do, eventually it was decided that it was an atmospheric effect that caused a tsunami, a small tsunami on the east coast of
Is
the
that
US.
something new and unusual? An
Yeah.
atmospheric tsunami?
Yeah.
Yeah, this is also, I mean, you guys, you never knew this at the time you went to school, but, studied this. But now you find yourself in the middle of climate change, and there's so many things that are changing and happening. I mean, unpredictable things that we never really studied before. Phenomena that are happening
Yeah.
now. And you're right in the middle of it. And you have the instruments to read it and understand it and maybe protect people. So what
I sure
about
hope so, yeah.
what about this kind of tsunami? Can you hear the sound of a tsunami before it comes? And is your acoustic equipment
That's a good
able to
question for
pick the
Bruce.
sound up before the tsunami gets here?
We acoustically, you would hear the earthquake.
Yes.
So it'd be the seismic signal that propagates through the water. I mean, it's just a big sound that goes through the water. But typically it's somewhat slower than in the sediment. So if you have a seismometer, you may pick up the signal before you pick it up from the water. But every little bit helps. And then obviously the tsunami itself, the surface wave signature is pressure. I mean, that's what you measure. And so that would be picked up by hydrophones. I mean, it's you're measuring pressure, you know,
Yeah.
so whether it's a hydrophone or a pressure sensor is.
Well, I now
Emergency.
remember, Jay, I don't know if it was the Fukushima incident or something before that, but there was this whole issue about how there are buoys out there in the ocean, and they're supposed to read seismic events and give you some advance notice about a tsunami. And there were a number of them in the North Pacific that weren't working.
Yes.
Yes. And it left us with less than optimal information.
Yes.
That's true. Also, for local tsunamis or something that occurs close to a coastline, those instruments really aren't entirely
Useful.
adequate. Adequate, let's put it that way.
Adequate,
You need to have tide gauges also that are between the event and the coastline, because those tsunamis create a lift in the ocean and then a drop, and so they migrate in both directions. And the wave that is coming toward shore, if you have to wait until you go 100 kilometers offshore to these dart buoys, which are the ones that Bruce is talking about, by then the tsunami's already swept the coastline of the nearest landmass. Whereas on the far other side of the Pacific, for instance, if it were in South America that this earthquake occurred, people in Australia and Japan and New Zealand would be well warned in time, but not folks on the coastline
Oh,
of Chile,
interesting.
which occurred in 2010.
So am I right to say that some of what you're studying, some of the equipment you're developing, can be better than what the Pacific Disaster Center has right now
Oh, absolutely.
in identifying a tsunami coming?
Maybe I'm digressing a bit here, but there's a new international global initiative to put sensors into commercial submarine telecommunications cables. So these cables that connect the continents and basically provide internet as we know it, they have little repeaters every 50 kilometers. And so now we're trying to get industry and business to include sensors, and the very simplest sensor is a pressure sensor. And the primary reason would be for tsunami detection. And so the idea is over basically 20 years, many of the cables that are in place get renewed or refreshed or go different routes or whatever. But over 20, 30 years, you'd end up with a global system with lots and lots of pressure sensors, temperature sensors, maybe acoustic sensors, and so on. So
I think you're losing your microphone, but
I think
I want to hear every word.
the advantage to that sort of thing too is that then you would have in real time information that you could use to predict where a tsunami might be going, but also you'd have a time sequence of measurements that would allow you much better models for figuring out how global warming or changes in currents or changes in distribution of, golly, almost any property of the oceans would be changing over time.
And there's a relationship between the changes in the ocean and the changes in the geology, meteorology over
Yes.
the ocean.
That's
Absolutely.
quite true.
So that if you had an accurate reading of the ocean, say at great distance, you'd be able to tell the weather at great distance.
I mean, the most obvious example of that are these big storms, in the Atlantic or elsewhere. Actually, the prediction of landfall and the intensity is actually tremendously better now than it was, a decade ago or longer.
Using underwater sensors?
Well, it's a combination. We now have the integrated ocean observing system, which includes like profiling floats that measure temperature, salinity as they go up and down. It's rather crude, but it's effective, and so there's a much better understanding of the temperature distribution near the surface and deeper, and that goes directly into these big storms. And there are other new platforms coming online. There's just like Brian Bingham's autonomous surface craft. There are other versions that are they use wave energy to move around, and solar energy and so on. And so likely those will be put in the Atlantic too. And yes, some of them might be destroyed by a hurricane, but some won't be, and they'll be able to report data that's much more localized and right at the surface, which is the most critical.
It sounds like your area is going to get, excuse the reference to temperature, but it's going to get hotter and hotter because people are going to need you. Commercial interests are going to need to know things that they cannot otherwise find.
Yeah. Well,
you'll be central in big processes that way.
Yeah, and one of the big sources of funding in this whole arena is oil and gas, and so.
Oh, sure.
So,
you can
for instance,
find oil
in the Gulf,
deposits.
well, it's protecting their investment. So, if a storm comes in the Gulf of Mexico, they have to shut down drilling and very expensive measures, and so they really want to know that weather as well as they can.
If we were going to have another incident like what happened in the Gulf of Mexico, would we be better off now than we were then?
Oh,
Absolutely.
Yeah.
And the other thing is too that the instrument sensing capability of remotely operated vehicles has improved tremendously. One of the things that happened during the Gulf spill is that when academics were able to go and measure the outflow from the pipe and discovered that the volume was so much greater than what had initially been reported in BP's estimations, that that kind of capability, Woods Hole's remotely operated vehicles,
Right.
other remotely operated big ones, powerful ones that have all of the sensors on them. This is the kind of thing that makes it possible for a rapid response that is much more effective than the kind of thing that you have to rely on the company to marshal when events like that take place.
Yeah, and you're also independent, rather than,
Right.
you don't have a vested interest, you have a
Right,
scientific interest.
Absolutely.
It's different. I was really pleased to find out that SOEST was involved in surveying the ostensible path of the undersea cable to Maui. What must be 3-4 years now
Yeah,
already. Because I think that's what Tom Apple always says. The university has to get out more.
Yep.
He said it right in that chair over there. So, it's great to see you guys have these jobs, and you can help the community and commerce and industry and whatnot. I'm just wondering though about the state of the art as it is. Unfortunately, from political points of view, we didn't build the cable yet, but, is there any question that we can build cables like that? This is not rocket science, is it? You can build
Yeah.
cables like
Yes,
that.
yes.
And the cables will last, and then you have equipment to go down and check the cables
Yes.
and ways to make sure the cables are functioning properly and all
Sure.
that. Yeah.
Sure.
My understanding is submarine cable here is sort of in the medium difficulty range. It's not, it's been done before, and you have to do it right and take precautions, but it can be done.
Yeah. Now, what about the, I don't know the answer, but I keep hearing that it's much more difficult to go from Maui to the Big Island because it's deeper. It's not full ocean depth.
No.
Because we didn't know until a few minutes ago just exactly how deep that was. but it's deeper. And my recollection is that the problem with that is that the cable laying ship, or the weight of the cable per foot is so great that when you drop it down off the fantail, it takes the ship with it.
Let's hope
This is
not.
very unpleasant. It ruins your whole day.
Well, it's a compromise between, diameter of the cable and the weight,
Yeah.
and therefore how much power you can take, and then you don't want it to break under its own weight. That's the basic limitation. So you have to use the very best steel, basically, as a strength member, and so on.
So is it available? I mean, can it be
Yes.
done
Yeah.
today?
Yes.
Okay.
Yeah.
Then we could do it if we wanted to do it. It's just, again, a political question.
Right.
Well, is that the way it's going? I mean, is the world going to be crisscrossed with cables across the ocean? I mean, we have them for internet, for sure. The Southern Cross and all those. There must be half a dozen of them around the Pacific. You guys watch those? Do you check those? Do you survey those?
Do you?
Well,
I don't.
I mean, because of my
If this is
Interaction with-
confidential or classified,
No,
it's
no.
okay.
Yeah. Because of my connection with Aloha Cable, and before I came to the University of Hawaii, I was at the University of Washington and helped design and plan the Neptune Canada system and the U.S. Equivalent to that off the Washington Oregon coast, so scientific cable systems. And so those now are becoming more common. And being deployed by other countries, and Japan is a leader in that also. So I think, I mentioned putting sensors into the commercial cables, and I think that's really where we want to go, because that
And
gets
you have that technology, the sensor technology.
Yes, that can be done now. I mean, it takes a little will and effort to do the first one, but getting business on board and all that.
Yeah,
But
sure.
it can be done. As far as transmitting power long distances, that's going to take, I mean, Maui, Hawaii, and so on, that's relatively short distance, but people are talking about from Iceland to the UK, because Iceland has a huge amount of power.
What's that,
possible.
300 miles or more?
Something like that,
Yeah.
and so that might be more challenging, but
Yeah.
it can be done. I don't see, crossing Pacific or things like that, but
You know, what's interesting with all the clean energy is essentially distributed. So do you need a cable? And the answer is, well, it's a political question.
yeah.
We had at this table, we had some people from Tasmania, Hydro Tasmania.
Yes.
They're very advanced. And it goes back to this interdisciplinary thing. It's not like the U.S. is necessarily more advanced than anyone else in earth sciences. You must deal with people all over the world and make friends and make jokes and have a good time and drink beer.
Absolutely. Or sake. A lot of sake.
That makes it fun. I'm sure it's more fun than you thought it would be back when.
No, actually,
You knew
it's
it was
been
gonna be
fun
fun.
all the way
Okay.
along.
Yeah, it has been, yeah.
I think Bruce and I both feel, incredibly lucky to be to have found a job that pays us to do our hobby.
Yeah, it's been fantastic.
What about funding? Is it sustainable funding wise?
Yes, we laugh.
Sorry, I said that.
Things have got tough. Most of my work is funded by the National Science Foundation, and it depends what field you're in. And one of the things that is really exciting right now is the interplay between geochemistry, so the chemistry of sediments and fluids and things on the oceans that you wouldn't have expected would be important for microbes, but the microbial communities that are the base of food chains often depend on reactions that are going on between seawater and rocks or seawater and sediments, and then the animals that subsist on these microbial communities, they grow around seeps on the seafloor, and we're finding these everywhere. We found the deepest one last summer when I was out on the James Cameron expedition, down at about 10,800 meters in the Mariana Trench. And the fact that the guys who are the microbiologists are finding that there are absolutely new types of microbial entities that exist there that had never been found before, that have chemicals in them that are the same sorts of things that are being used to treat Alzheimer's.
Who knows where that could go? Yeah.
Absolutely, who knows where that could go.
Well, I'm really delighted to talk to you guys. It's been a great conversation. I want to do it again and again with SOEST. I think SOEST is great.
Great.
And I want to sign up to go to school there.
Oh, yeah.
So I want to see if I can be as lucky as
Forever
you guys.
young. Yes.
Yes, lifelong learners.
That's Bruce Howe and Patty Fryer from SOEST, the School of Ocean, Earth Science and Technology. This is ThinkTech Talks. We've been talking about ocean science in the 21st century. And we're going to take a break now, and in a minute we'll be back with Kali'i Akina talking to us from Shanghai, why not, by Skype on E Hana Kako. Thanks for watching. Thank you guys.
Oh, aloha.
Aloha.